Okay, let's dive right in. Welcome to the Archaeological Dig, the ultimate explainer, where we are going to completely uncover the examiner's secrets for Cambridge computer science. And look, whether you're tackling syllabus 0417, 0478, 0983, 0984, 2210, or facing the advanced challenges of AS and A-Level 9618, the core concept we are dealing with today is universal, simple, and incredibly powerful. We are going to uncover the hidden clues buried deep inside the exam question, and layer by layer, we're going to reveal the absolutely perfect answer. Picture this, a real Cambridge computer science past paper question, like those notorious ones from the 9713 or 9618 papers, flashing right in front of you. A timer is ticking down. The tension in the exam hall is literally palpable. Now, we typically see two types of candidates here. First, we have Alex. Alex is the overloader. Alex knows every single raw computer science fact, but just dumps them onto the page with zero actual analysis. And then we have Sam. Sam is the rusher. Sam completely panics, rushes through the complex logic gates, and totally misses the specific command word requirements. Constructing logic expressions from complex circuits is a universal struggle for both the Alexes and the Sams of the world. Without a rock-solid strategy, the pressure simply takes over. Today, we are going to completely rewrite that narrative, fix those flawed answers, and build a foolproof, top-tier system.
Now, what's really fascinating here is that the principal examiner reports tell us exactly where students are losing their marks. The examiners explicitly state, in no uncertain terms, that this specific topic is a massive, massive stumbling block. Students look at a complex, tangled network of logic gates, your standard AND, OR, NOT, NAND, NOR, and XOR gates, and they just freeze. They panic. Like Sam, they try to jump straight to the final Boolean expression at the end of the circuit without documenting a single step of their journey. They treat it like a total guessing game instead of a systematic logical derivation. But here is the ultimate secret you need to realize. Those examiner reports, they aren't just complaints. They are literally a treasure map handed straight to you. By understanding exactly what the examiners are frustrated by, like Alex overloading facts or Sam skipping steps, we can reverse engineer the perfect response. We're going to take those red pen marks, all those missed opportunities, and transform them into brilliant green check marks and full marks.
So we really need to dig into the root of this question and reconstruct the perfect answer, layer by layer. Why exactly do students struggle so much when a circuit doesn't look exactly like the perfectly neat one in their textbook? Well, it's because they lack a systematic, adaptable framework. They have the raw knowledge locked away in their heads, but they just don't know how to deploy it when the context shifts even slightly. A massive issue here is ignoring those crucial command words. Listen, if a question specifically asks you to construct an expression, but you simply describe the behavior of the individual gates, you lose marks. It's that simple. If it demands that you evaluate a circuit's efficiency and you just mindlessly write out its truth table without any commentary, you get an absolute 0 for analysis. We desperately need a system to decode these command words instantly under pressure.
To fix this, here is our step-by-step roadmap for decoding this incredibly complex topic and transforming it into an actionable strategy. First, we'll tackle the logic circuit challenge. Second, mastering method marks. Third, 3 common examiner warnings. Fourth, critical analysis and evaluation. And fifth, your exam strategy blueprint.
Section 1. The Logic Circuit Challenge. Let's start with the absolute core theoretical foundations you need to master logic expressions.
Top-performing students, the ones securing the highest grade boundaries, don't just blindly memorize. They demonstrate connected understanding and they reference cross-topic connections to achieve significantly higher marks. To truly excel and elevate your answers, you need to understand frameworks like PEAL. That stands for Point, Evidence, Explanation, and Link. An elite student knows that logic circuits aren't just isolated diagrams floating in a vacuum. They deeply understand the causal relationships. They know exactly how changing a single input from a 0 to a 1 cascades sequentially through a complex web of NAND gates to flip an output. Furthermore, they use cross-topic integration brilliantly. They can confidently link a logic circuit expression to core CPU architecture, specifically explaining how the arithmetic logic unit, the ALU, uses half-adders and full-adders to actually perform binary arithmetic. That level of deep interconnected understanding is exactly what examiners are desperately looking for when they award those top bands.
Cambridge assessment objectives precisely target these 3 distinct cognitive domains, so your foundational knowledge must easily and seamlessly transfer to entirely unfamiliar contexts. Let's actually do a quick interactive check right now. I'm putting 30 seconds on the mental clock. Think fast. Imagine an exam answer that simply says, an AND gate outputs 1 only if both inputs are 1. Which specific domain is that? Right, that is pure knowledge. Now imagine a much better answer that says, in the specific automated greenhouse system, the AND gate ensures the sprinklers only turn on if the temperature is high and the soil is simultaneously dry. Which domain are we hitting now? Exactly, that is application. And what if a top-tier answer discusses how strategically replacing 2 AND gates and an OR gate with universal NAND gates fundamentally optimizes manufacturing costs and reduces hardware complexity? That is pure analysis. To secure the perfect score, you absolutely need to hit all 3. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now, Shadha.
Section 2, Mastering Method Marks. Next, let's move to our procedural framework and look at how examiners actually award the points on the page.
So, the absolutely crucial point here, the thing that separates an A from a C, is that you must show your clear working. Because examiners heavily reward the process itself. Think about it realistically. Constructing a massive Boolean expression from a multi-level logic circuit is genuinely hard. Under exam conditions, it is so incredibly easy to drop a single not bar or misplace a crucial bracket. If you are like Sam and you just write down the final answer at the bottom of the page and it happens to be wrong, you get 0, nothing. But if you actively label the intermediate points on the actual circuit diagram, let's call them node X and node Y, and you deliberately write down the algebraic expressions for those individual nodes before combining them, you secure the method marks. The examiner clearly sees your logic, sees your structural process, and rewards you for the correct theoretical steps taken, even if a minor silly transcription error occurred at the very final hurdle. And this brilliantly illustrates the exact standardized sequence you absolutely must follow to secure those method marks on literally every logic circuit question. Step 1. Identify key elements. Do not just stare at the paper. Literally take your pen, circle the logic gates, and clearly label the intermediate wires. Step 2. Apply relevant principles, pulling in your Boolean algebra rules or De Morgan's laws. Step 3. Execute the analysis with crystal clear working. Write down the sub-expressions distinctly. State clearly, node X equals A and B, node Y equals not C. Step 4. Verify your results. Listen to me, this is massive. Use a super quick trace table or truth table to test your final unified expression against the original circuit using just a couple of test inputs. It takes seconds, but saves grades. Step 5. Present in the precise format requested by the specific command word. If you rigorously follow this blueprint, your marks will absolutely skyrocket.
During that entire process, your specific data interpretation skills will be heavily tested as you continuously extract, calculate, and conclude. Right now, I really want you to visualize a timer on the screen counting down from 60 seconds. This is challenge 1. You are looking at a highly complex binary truth table provided in the exam. You don't just passively stare at it. No, you actively and aggressively extract the specific rows where the final output is 1. You then use those specific active rows to perform your calculations and systematically formulate a complete sum of products expression. Finally, you draw your solid evidence-based conclusion by strategically minimizing that clunky expression using your rules of Boolean algebra. That active, relentless, 3-step data interpretation is exactly how top-tier, grade A candidates process raw information under intense pressure. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 3. 3 common examiner warnings. Now let's uncover the absolute most dangerous pitfalls hidden in past papers, straight from the examiner's secret playbook.
Pay close attention because these are the top 3 mistakes candidates make year after year, straight from the principal examiner reports. Let's look at challenge 1, the data scan. Imagine a highly complex logic circuit diagram that is controlling a nuclear reactor's critical cooling system. What's the core trend here? The massive mistake candidates made is totally confusing cause and effect. They might write something like, the alarm rings, which causes the internal temperature to rise. Completely wrong. The logic circuit physically evaluates the rising temperature inputs in order to subsequently trigger the alarm output. Secondly, they completely forget edge cases. What exactly happens if both sensor inputs completely fail and simultaneously read 0? Does the system default to safe? And thirdly, the absolute biggest sin you can commit in Cambridge exams, providing generic, memorized textbook definitions instead of meticulously linking your knowledge back to the specific nuclear reactor context provided in the prompt. This side-by-side comparison perfectly shows the classic mistake in action. Remember, you must always link every single point to the specific context provided in the question. Welcome to Challenge 2, Find the Flaw. Think about a typical generic answer. This is our friend Alex's style. It says, an XOR gate outputs true and the two inputs are logically different. Now, is that statement factually correct? Yes, absolutely. Does it score any marks at all? 0. Why? Because the exam's command word explicitly asks to explain the logic of a car park barrier system. Now consider an optimized context-linked answer. This is the transformation. It says, the XOR gate ensures the car park barrier only opens if a ticket is inserted or the sensor detects a car, but crucially, not both simultaneously, thereby preventing critical system errors. Boom. That is specific, that is mapped directly to the scenario, that is exactly how you secure maximum marks.
Section 4, Critical Analysis and Evaluation. Let's move to the next level and see how all of this builds into those tricky higher-order assessment objectives, where you must evaluate alternatives and rigorously justify your recommendations.
When you are tasked with evaluating algorithm or circuit quality, you must specifically identify time complexity, space complexity, and edge cases, and then directly analyze their real-world effect on performance. Now it's time for Challenge 3, Speed Writing. I am officially putting 30 seconds on the mental clock. Your task is to mentally construct one totally perfect, Peel-structured evaluation paragraph for a logic circuit. You simply cannot just say, Circuit A is fundamentally better than Circuit B. That's weak. You have to use the critical factors we're looking at right now. For example, for a logic circuit implemented purely in software, you need to confidently explain exactly how redundant logic gates increase the time complexity and noticeably slow down the execution speed. You need to explain how failing to properly account for extreme edge cases, like all input sensors triggering a 1 simultaneously, can completely crash the system stability. Your explanation must be rigorous, it must be technical, and it must be precise.
Furthermore, if the command word asks you to compare approaches, you must burn this exact formula into your brain. You must identify both similarities and differences. You must use comparative connectives, and it must be backed up by hard evidence. Let's say you are asked to compare a physical hardware logic circuit with a software-based logic simulation. Do not, I repeat, do not, just write 2 entirely separate paragraphs describing each one in isolation. You must use comparative connectives like whereas, conversely, or indirect contrast. For example, a top-tier sentence looks like this. Both approaches utilize Boolean logic to mathematically determine the output state. However, the hardware circuit processes all inputs concurrently with near-zero latency, whereas the software simulation evaluates expressions sequentially, which inherently introduces a measurable processing delay. That is exactly how you synthesize complex information. You provide the concrete evidence, and then you draw a definitive, undeniable conclusion about which one is better suited for a time-critical application.
Section 5, Your Exam Strategy Blueprint. Finally, let's assemble all these analytical clues and rules into your ultimate, unbeatable exam strategy blueprint. Your algorithmic thinking should always follow this exact chronological path, moving from step-by-step decomposition all the way through to rigorous testing. Let's practically apply this timeline to our logic circuits. First, decomposition. You take that massive, intimidating circuit and break it down into individual, manageable gates and intermediate sub-expressions. Second, data structure selection. In this specific context, you must decide strategically if you're using a basic truth table, a complex Carnot map, or pure Boolean algebra to best simplify your extracted data. Third, efficient implementation. You carefully write out your final simplified Boolean expression, ensuring absolutely proper use of grouping brackets and not bars over the correct variables. And fourth, rigorous testing. You take a hypothetical test case, you run it step by step through your written expression, and you meticulously verify that it perfectly matches the output of the original physical circuit diagram. A truly fantastic way to recall this incredibly complex procedural framework when you are under severe exam pressure is to build your very own memory hack, a mnemonic derived from the first letters of the core steps. We talked about 5 incredibly specific steps earlier: identify, apply, execute, verify, present. IAEVP. You could use something simple and memorable like intelligent analysts evaluate valid programs. Create whatever funny or weird mnemonic actually works for your specific brain. The entire point here is to have a rock-solid cognitive anchor.
so that when exam anxiety inevitably hits and the clock is ticking down, you don't freeze like Sam. You just calmly write down your mnemonic on the corner of the rough paper and you systematically, ruthlessly, follow your own perfectly structured process to grab every single mark. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
So, now that you finally have the complete examiner's playbook decoded and laid out in front of you, what specific actionable step will you take today to ensure you properly document your process and secure absolute maximum marks on your very next practice exam? Are you going to commit to actively labeling intermediate nodes on every single complex diagram you see? Are you going to absolutely commit to writing those quick trace tables to mathematically verify your complex Boolean expressions before you move on to the next page? Remember, simply having the knowledge in your head is totally useless unless you actually apply the strategic framework when that exam timer is relentlessly ticking down. So, deeply think about your current weak spots, intentionally build out your structural framework using Peel, and go tackle those logic circuits with absolute, undeniable confidence. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.